I thought you were listening. There was a mute button here. That's it. Okay, we'll start now from the beginning. So, today we'll continue with the quantum mechanics. You had three sessions before, and we are continuing with the quantum mechanics. And today you are going to understand are going to understand what are wave functions and probability density along with the normalization. Okay. Oh. So now start with wave function. What is a function? You know that a mathematical function y is equal to f of x. Used to write mathematically y is equal to f of x. Y is the dependent variable and x is the independent. You know this mathematically. So it's a function of some dependent and independent variable. Our wave function here, it's a function of x, y, z and t. Here x, y, z represents, they are the position coordinates, that's the space coordinates, t is the time. So wave function is a function of space coordinates and time. So now what do you mean by a wave, or what are waves? Waves represents the quantities that vary in a medium, isn't it? You write waves. Waves that represent the propagation of disturbance in the medium. So waves are some quantities. You will see that there is periodic variation of a quantity with respect to time and position. So waves in general defined as they are the quantities that vary periodically with position and time. You know this. So you know some examples for waves also: sound waves, electromagnetic waves, water waves, etc. and so on. You know the sound waves. What is that quantity that varies in sound waves? It is the pressure columns, the pressure, the variation. It is the compression and rarefaction of the medium, the pressure difference that varies in the medium. So that's how the sound propagates. So in sounds, it is the pressure that varies periodic. If you look at the water column, water wave, these waves, how do you observe this? Imagine you are standing near a calm pond, and there you throw a stone into it, and you will see immediately the ripples gets generated, and this ripple starts moving outwards. It starts moving outwards, and you will see that it is the height of the water column that is moving up and down. So in waterways, it is height of the water column moving up and down, that causes the ripples. So the here in waterways, it is height of the water column that is varying periodically. Similarly, if you go for electromagnetic waves, it is the electric vector and the magnetic vector that varies periodic in nature. Electric vector E and magnetic vector, they are varying periodically. That results the electromagnetic waves. You know that. So in any wave, the quantity that varies periodically in nature, isn't it? So if you take matter waves or look at the de Broglie waves, so the quantity that characterizes the matter waves, the quantity that characterized the de Broglie waves are called the wave function. Wave function is the quantity that varies periodically in matter waves or the de Broglie waves. Understand? The wave function in matter waves, this is the quantity, that is wave function is the quantity that varies periodic in nature in matter waves and de Broglie waves, that is given by the term wave function. Notation is psi. It's the Greek symbol psi. When you look at this wave function with respect to the material particles, the microscopic particles, that is with respect to the matter waves, this function, wave function, is a complex quantity. This function psi is not an ordinary quantity, it's a complex function. You know, a complex number, a function or a value is given by psi. If you take psi as a complex number here, that is equal to a plus ib, a plus ib, where a and b represents the real terms, I is imaginary. So a complex number is represented by a plus ib, where I is imaginary. You know that I is equal to root of minus 1. Since this wave function is having imaginary in it, there has an imaginary in it, therefore psi by itself has no direct physical significance. You cannot see psi, you cannot observe psi in the physical world directly. You cannot feel the wave function directly. because of its imaginary term in it. Therefore, it is not a physically an observable quantity. In the physics, in the world, physical world, you cannot directly see the wave function psi. Then how to feel this psi, how to feel the wave function psi, that is given by the probability density. I'll explain in the next slides. So the value of the wave function psi can be seen as its probability density. Okay. So the value, the psi is a complex number. So now I want to say in the physical world, I'll convert this psi into a real quantity and I call that it is a probability density in the physical world. We'll see that. And you know that here we are dealing with quantum mechanics, and whatever the measured values are all nothing but the probable values. Whatever you find in psi or probability density, they are all probabilities, they are probable values. I told you that since I is a complex number by itself has no direct physical significance, you can't see it uh, in the physical world. In order to see the psi, you have to go for probability density. Now, how the probability density is defined? It is defined as the likelihood of finding the particle associated at a particular point xyz in space at the time t is related to the modulus of xi square there at the time t. I'll explain this. I'll go to a few slides and I'll come back to this. See, you look at the slide here. I told you the wave function psi is a complex number. Psi is equal to a plus ib, where a and b are real quantities, I is imaginary quantity. And since psi is having a plus I having I, it is not a physically meaningful quantity. You will not observe it directly, no direct significance. If you take the conjugate of this wave function, psi star is equal to a minus ib. So you got psi, take its conjugate, complex conjugate, it is a minus ib. Now you do the product of these two, psi and psi star. When you take the product of these two, you will see that it is only a square plus b square. This I square will go. Okay, I square gets, you know that mathematically. So this will become a real quantity. So now psi is a imaginary quantity. So it is not physically an observable one. So in order to see in order to get into the physical world, you take the product psi into psi star. It becomes a real quantity. Now it is physically an observable one. Okay, it becomes a physically an observable one, and we call this product of psi into psi star is equal to modulus of xi square, and we call this is probability density. Okay, same as product of psi into psi star is equal to the modulus of psi square, we call it as a probability density because we are seeing in the physical world. So it is an observable quantity now. So earlier psi alone is not an observable, physically not an observable quantity. Now psi into psi star becomes an observable quantity. So it can be, you can feel it, you can see that. Okay, I'll come back to this slide. I want to go back. So you are there here, isn't it? So the value of wave function psi is a imaginary quantity. Therefore, I want to see that in terms of in the physical world. I want to say this in the physical world. So therefore, what I do, I mathematical trick psi into psi star, that is equal to modulus of psi square, that will become the probability density. Now how to define this probability density? It is defined as the probability of finding the particle. It is defined as the probability of finding the particle in the given region of space xyz, and that time t is proportional to modulus of xi square. Okay, p proportional to modulus of xi square, that is the meaning of probability, that's the definition probability density. So now you know that mathematically speaking, the probability is physically an observable quantity and whose values varies from 0 to 1. If the probability is 0, what do you mean by that? It corresponds to the absence. It means if the probability is 0 means that event do not going to happen, the event will not happen at all. If the probability is 1, it means that that event certainly going to present. It represents the presence. Probability 1 represents the complete presence and probability of 0 represents the complete absence. And from physics point of view, you know that you already studied, understood Heisenberg uncertainty principle. You don't have the completeness, you don't have the certainty, isn't it? So you don't have complete certainty, you don't have complete, that is complete 0, 100% or 0. Therefore, in physical world, the probabilities are going to be anywhere between, that is greater than 0 and less than 1. So the extremities are 0 and 1, they are the theoretical values, but practically speaking it's more than 0 and less than 1. So it is 0.001 something like that, and maybe at the end, I mean to the extreme end, 99.999 something like that. You cannot write 100% or you can take 0 as per the Heisenberg's uncertainty principle. So this is introduced by Max Born in the year 1926. The concept of this probability interpretation of the wave function is given by Max Born in the year 1921. So from the mathematics point of view, probability is anywhere between 0 to 1. From the physical point of view, in the physical world, it is more than 0 and less than 1. Okay. So now P is a real quantity. Probability density is a real quantity. And if you look at the wave function psi, you know the wave function psi, it has got the both the positive values and negative values, isn't it? So phi, the value of phi, if you write a wave, it is having both on the positive side and got the negative side. But probability cannot be negative. Probability cannot be negative. It is always positive. So you should take only on the positive side of the this one. So therefore, the probability of finding the particle in any given volume dV is proportional to P proportional to modulus of psi of xyz square into dV. And here if you take psi alone, it represents the wave amplitude, the wave amplitude, and if psi into psi star gives you the probability density. See, look at this diagram. You already, once you came to this slide, see here the blue one represents the wave function psi. Psi is equal to a plus ib, and the red curve represents, it is psi into psi star, that is equal to a square plus v square. It's purely a real value. The blue got the negative values and red got only the positive values. You look at the second diagram, the blue is varying like sine waves moving up and down on both positive and negative sides. So negative values of probabilities are meaningless, and we have used the trick, since if you have only psi, it is being imaginary, it is not an observable quantity. Therefore we used mathematical trick, psi into psi star, it becomes real quantity. If you take these values, you will see it is only on the upper side of the x, so it got only the positive values. The red curve represents the probability densities, probable values. Okay. I told you that probability is anywhere between 0 to 1. And here imagine that you are finding the particle. You are trying to find the particle. Okay. So you have chosen some region of space. So in some region of space, you are trying to locate the particle. So you have to go with the initial assumption that particle is there in the space. Therefore, I am going to find it. That is the initial this assumption. If you have an initial assumption that particle is not at all present there in the region of given region of space or the chosen region of space, and you are going to try and you are trying to find the particle, means it is meaningless, isn't it? Therefore you initially start with, you want to find a particle, means the particle should be there in the space. So you start with, imagine that the volume you have chosen, the region of the area, the region of space you have chosen is such that the particle may be present. With that intention you go. Therefore here look at the integral, it is minus infinity to plus infinity modulus psi square dv is equal to 1. It means that you are going to find the particle assuming that it is there in the space. Therefore probability will be ultimately it should be 1, and the space you have considered here is minus infinity to plus infinity. Okay, here don't this confused. Infinity means it doesn't mean that you have considered entire universe or world, something like that. It's not so. Whatever the region you have considered, it is your limit of space. Imagine that is where you are trying to find. So the limits you apply that space itself minus infinity and plus infinity. Suppose the particle is not present in the given volume, the volume chosen dV, then you may extend the this region of space. You may extend and try to find it. If you are not able to, again not able to find the particle, means you extend further like that. So the limits of the integration is minus infinity to plus infinity, and modulus xi square is represents the, it is the probability of finding it in the volume dV. The right hand side is equal to 1 means, so with that given region of space you have found the particle. That's what the meaning. Okay. Since the particle is certainly somewhere in space, the probability P should be 1, and the integral of P over the entire space must be unity. Therefore, we'll take the integral minus infinity to plus infinity modulus xi square dV is equal to 1. Okay. So you have seen that we already got some idea that phi, this single psi, has no physical significance because of its imaginary quantity. But when you looked at modulus xi square, the I will go, it becomes a real quantity that represents the probability of finding the particle in the given region of space. Okay. So you have chosen some space and trying to find the particle, and it is not that always the particle is going to get, isn't it? See, you have chosen some region of space and you can't say that always the particle is present. If you are getting always the, I mean, you are sure that you are going to get the particle, the probability is 1, isn't it? So in most of the cases, most of the regions you have chosen, the particle may be not completely be present there. Okay. So there may be the probabilities are less than 1 also, isn't it? If it is exactly 1 means it is 100% finding the particle. If it is 0 means particle does not exist at all. So the particle is somewhere anywhere between 0 to 1. In most of the cases, the above integral will not be unity always, will not be unity always. So it is having some variation values 0 to 1. So therefore, this function, the value, the wave function involves a constant that is hidden in the wave function. You will understand in the next slide. So look at this one. See here, psi n, that is x y z t, and the left hand side is equal to c psi of x y z t. Okay, then only it is balanced, because it is not sure that all the time you are going to get the particle. So the value of c is not all the time is equal to 1. Therefore, it has some value, it is other than 1, therefore it is c. Okay, to balance the equation, psi of n x y z t is equal to c of psi x y z into t, which satisfies, look at the second expression, that is minus integral infinity to plus infinity psi n x y z t modulus square dxy dz is equal to c square, and the integral of minus infinity to plus infinity, and here again the subscript n is there. So okay, you take out this subscript, it is a printing mistake. I'll show this one, I'll make correction. uh, 1 minute. This psi n there, no, psi n not there. Okay, psi n it is not there, only modulus of psi xyz t square into dx dy, like that way you should consider. Okay, don't take again here also psi n, it is not there, some mistake, typing mistake. Therefore, the psi of n xyz t whole square represents the normalized function, and c is called the normalizing constant, and the overall process is called the condition, above condition is called the normalization condition. Okay, so in any this evaluation of the wave function, you need to find the value of the constant c. The constant c involved in the function should be evaluated. This process of evaluation, the process of evaluation of this constant c that is hidden in the wave function is called the normalization. Okay. So now, what are the these conditions for the wave function? If you say the wave function that is satisfying under the this quantum mechanics should have certain properties. An acceptable wave function must be satisfied. How it is satisfied? It must be a normalized one. First of all, it should be a normalizable wave function. Okay, then this wave function psi must be finite. I'll explain this. Psi must be finite. It means that you are choosing a region of space that is x, y, z, that is plus infinity to minus infinity. It means you have chosen certain region of space. There you are trying to find the particle, isn't it? So the function should exist within this given region of the space. The function must exist within the region of the space you consider. Then only it is accepted, then only there is a value for the wave function. Okay, psi must be infinite means it means that the wave function should exist in the region of space you have chosen it. If suppose the region of space you have chosen such a way that wave function do not exist means you can't take that particular region of space, so you must confine a region of space such a way that the wave function should exist. That's what the meaning of psi must be finite within the given region of space. And the point number 2, it must be single valued. See, it is, imagine that it is a wave that is going within the region of space. Then at any region of any point in the space you consider the wave is traveling, it should have a single probability, isn't it? So at any point of the wave you that is within the region of space, the wave is moving means at that point you should have only one probability. There must be only one probability it should exist. And if you go to the next point, immediate next point, there may be another probability. It's like that, as the wave that is propagating through this region of space, at a very point wherever it goes, it has a single value of probability, single probability, and it kept on going it. Suppose the wave function does not exist somewhere in between means it is the forbidden region. So you don't choose such a region where the wave function do not exist at all. So you must choose a region of space where the wave function exists, and wherever the wave is moving it should have one probable value for its probability, and it is continuous over the entire region of space. That's the meaning of psi must be continuous. And the fourth point is its partial derivatives once again should exist. It means that if imagine y is equal to f of x, you have a function y is equal to f of x. If you have some function, this dy by dx represents the slope. So if there is a wave at any point you choose, you find out the variation of dy by dx. If there is a value for dy by dx, then you say there is a value of slope. So there and that point wave exists. If the slope is 0 means the point where you don't have the wave continuing. Okay, so you choose since it is a continuous wave that is propagating in the medium, at wherever the point you consider, their slopes must exist. Its partial derivatives del x, that is del psi by del x, del psi by del y, and del psi by del z with respect to these coordinates, x, y, z coordinates, once again should exist. Their values are finite, continuous, and single valued everywhere. That's what the properties of the wave function, or it is also called the characteristics of the wave function. Okay. So now such wave functions are called the well behaved wave functions or the eigen functions. So the wave function that satisfy the conditions, the 4 points that is shown in the previous slide, they are called the well behaved functions. They are accepted ones, and these functions are called eigen functions. Once you know the eigen functions, it is easy to evaluate the and easy to get the eigen energy values for the particles. Okay. So this is a bit more theoretical today. So more mathematics we taught, try to understand today. And